Okay, so let's start with this class with an inequality you will need for one of the exercises, which I didn't cover before. So this is so, uh, useful inequality. Let's try with a different pen. So a useful inequality, so theorem. Jensen's inequality. So it says the following thing: if u going from R to R is convex, and x is a random variable, then the expectation of u of x is bigger or equal than u of the expectation of x. Okay, so one of the things that happens with this inequality is that sometimes you forget which way it goes. The usual way of realizing how this goes is by thinking of u. So an example, for example, u goes from R to R, u of t is equal to t squared. Okay, so this is convex. And so one of the things that we should know from the Cauchy-Schwarz inequality is basically that the expectation of x squared will be bigger or equal than the expectation of x squared. This is by Jensen's or Cauchy-Schwarz. Okay, so this is the case. So Cauchy-Schwarz case x equals to y. What else did I want to say about this? So yeah, maybe this is not completely clear, but one of the ways of thinking of this, or at least that I think of this, is just if you take the integral of a function dx and the squared of the integral will always be bigger or equal than the integral of f dx squared. Okay, so this integral here could be equal to 0. So now if you take 0 squared, because there is a cancellation, you take 0 squared, you get 0. But in this case, you're taking the absolute value squared. So this will always be positive, while this could actually vanish. So that's a way of remembering this inequality. So in general, like, what are the examples of this? The one is the x squared. The other example is u of t is equal to e of t. This is convex. And another example is u of t is equal to modulus of t. And another one would be u of t, which is equal to the maximum between 0 and t. And this is the case in which you have this function here. Sorry, this is t, this is u of t. Okay, so it's 0 and then it goes up. And so for all of this, we can apply Jensen's inequality and get that the expectation of e of x is bigger or equal than e of the expectation of x. And similarly, the expectation of the absolute value of x is bigger or equal than the absolute value of the expectation of x. And the expectation of x times the indicator of x positive, okay, which is this function here, is bigger or equal than e of x times the indicator of the expectation of x positive. Okay, so this thing here is applying for this function here. Okay. Yeah. So now what we need to do is to give a proof of this. So I guess proof. And let's start with like a reminder of convex functions. U from R to R convex, if and only if. And so I'm going to assume that U is smooth, but usually convex functions are regular, and you can actually get if the second derivative U second of t is bigger or equal to 0 for every t in R. So basically a convex function looks something like this. Okay, so it has to, another way of looking at convexity is that like the upper level set is a convex set, so you can connect it by lines. All right, but one of the main properties of convex functions is convex functions lie above their tangent lines. Okay, so let's say we have a point here. So let's have a point here, which we are going to call A. Do I want to call it A? No, probably I want to call it X star or T star. So at T star, here we consider the tangent line. Okay, so where this green thing, the line at T is going to be equal to U prime at T star times T minus T star plus U of T star. Okay, so another characterization of convex functions is if and only if U second is positive, if and only if it lies above its tangent line. Okay, and so the tangent line at T star is given by this thing here. All right, so in particular, so we consider, we take the specific case that T star is equal to the expectation of x. Okay? So T star is the expectation of x. So U is a function from R to R. Expectation of x is a number in R. And now we take this T star to be expectation of x. So then what we get is that U of T is bigger or equal than U prime evaluated at expectation of x times T minus expectation of x plus U at expectation of x. Okay, so now this function is bigger than this function. Now this is a number. And so this guy is a function, this L of E of x. Here this would be L of t star. L of E of x goes from R to R. Okay, so by this inequality, we can compose these two functions with the random variables, and we get that U of x, which is a new random variable, is bigger or equal than L of Ex at x. Okay, so these are two different random variables now, and what we can use is the properties of the expectation to say that the expectation of U of x is bigger or equal than the expectation of L expectation of x evaluated at x, like this. So now to finish the proof of this theorem, so on the left hand side we have expectation of U of x. Now we need to see that the right hand side is literally U of expectation of x. Okay, so now we use linearity. We use linearity of expectation to obtain. Okay, and so here basically what you do, you take the expectation on the right hand side. This is a constant, it comes out. This t is replaced by x. So when we take the expectation, you get the expectation of x. This is a constant, so it comes out as the expectation of x. So this term here disappears. Okay, so the main point to realize is that this term, when you take expectation, you use the linearity to get that this is equal to 0. And now when we take expectation of this constant term, you just get U of expectation of x. We use linearity to obtain that this thing here is expectation, U of expectation of x, which is less or equal than the expectation of U of x. Okay, and that's the proof. All right. So there is one of the exercises that you will need to use Jensen's inequality, so it's good that you have seen it in class at least. Okay, so what's next? So what we're going to start seeing in this class is convergence of random variables So one of the things that we have said a few times in this class is that, for instance, if we flip a coin a lot of times and we take averages, we are going to see that the averages of the coin flipping will be converging to a normal random variable. So one of the things is how can we measure distance between random variables? Okay, convergence of random variables. How do we measure distances between random variables? So, for instance, let's start with a definition. We say xn converges to x in distribution Okay, so here xn, this is xn, is a sequence of random variables. We say that a sequence of random variables xn converges to x in distribution if the probability that xn is less or equal than x converges to the probability that x is less or equal than x. So the limit for every x, so for every x that is a point of continuity of px less than x. Okay, so this is the distribution function fx. So so this is the distribution function for xn. So morally what we have here is fn. So fn looks like something 0, 1. So fn looks like something like this. And then f maybe is a continuous thing. So the idea is that fn, even if it's a discrete random variable, you can be converging to a continuous random variable just by checking that this distribution converges to that distribution. Okay, so let's give an example of something like this. So what is an example? Let's say that xn is equal to a uniform distribution in the set 0, 1 over n, 2 over n, 3 over n, all the way up to 1. Okay, so these are n plus 1 points. So if you look at fn, it will look like something like this, but between, so here it would be 0 and here it would be 1, and all of these breaks here are at 1 over n, 2 over n, and so on. And in the limit, what you expect is that you get a straight line. Okay, so if you take this uniform in this thing that becomes smaller and smaller, in the limit n to infinity, this converges to x, which is a uniform number between 0 and 1. Okay, so this notion of convergence allows you to converge from something that is discrete onto something that is continuous. Okay, we are not going to use this in this class, but that's it's a good way of saying that this is a really general notion of convergence, so you're not stuck in one of the classes of random variables. Okay, so this convergence induces a notion of distance. So let's change the page. So we have the notion of total variation distance. Total variation distance. The total variation distance between, let's say, two variables x and y is equal to the supremum over all the subsets of R of the probability of the absolute value of the probability that x is in A minus the probability that that y is in A. Okay, and so here x and y are random variables which are not necessarily defined on the same sample space. Okay? So the claim is the only thing that you need to know is what is the value of x being in a particular set versus the value of y being in a particular set. And here we are taking the sets in R, and here we again should add the condition Borel measurable, but don't worry about this. So morally, this is all the sets in R. And now you're asking what is the difference of the probabilities of x and y being in the same set. So, for example, so one of the things is taking a x, which is equal to minus infinity x, close, then dTv of a sequence xn x goes to 0 implies that xn converges to x in distribution. Okay, so here we were asking that this is continuity points for these points x. This is the sort of minimal requirement that we can ask for convergence. Total variation distance is a bit stronger. Okay, so total variation distance is stronger than convergence in distribution. Okay, so the next thing that we're going to be looking at is couplings. So the idea is that x, comma y are not necessarily, so x, comma y are not necessarily defined on the same sample space. Okay, so I'm repeating this because it's fairly important. So the idea is that what we have is that x is going from, let's call it omega x to R, and y is going from omega y onto R. Okay, and so here I'm saying omega x, but here I should mean omega x fx p x. So that's saying that I have a probability triple that is associated with x, in which x is measurable, and I have y, which is associated with another probability triple. So the idea is that sometimes it is interesting to connect x and y through the same probability triple so sometimes it's interesting to connect x and y through the same probability triple, maintaining its distribution properties. Okay, so morally, what we are saying is it's sometimes for a matter of proofs and things, what it makes sense is instead of considering of considering x and y, we can consider x prime and y prime such that x prime comma x prime is going from, let's say, omega prime onto r, and here I'm thinking omega prime, f prime, p prime, and similarly for y prime is going from the same sample space onto r, such that the probability that x is in A is equal to the probability that x prime is in A for every A subset of R, and similarly the probability of y is in A is equal to the probability of y prime is in A for every A subset of R. Okay, so the point is we want to come up, sometimes it's useful to come up with a new random variables from a new space. Okay, so omega prime, f prime, and p prime is a new probability triple we come up with ad hoc. So ad hoc just means that we come up for the specific purpose that we have in mind. Okay, so let's look at a lemma. Let x, comma y be random variables. Then the total variation distance between x and y is equal to the total variation distance between x prime and y prime for every x prime similar to x, and for every y prime similar to y. Okay? Moreover, we can bound the total variation distance between x prime and y prime is less or equal than moreover, if x prime and y prime are discrete random variables, we can bound. So here we need the property of being discrete. If x prime and y prime are discrete random variables, the total variation distance is less or equal than 2 times the probability that x prime is different from y prime. Okay, so first of all, the first part of this lemma, that the total variation distance is the same between x and y and x prime and y prime, makes sense out of this property. Okay, so the concept that the probability that you're in a specific set in R is the same as the probabilities for x and y, and if we go back to the total variation distance, in this case is just given by the supremum of A in R of the probabilities that x or y are in this particular set. So if we preserve these probabilities, then this distance is the same. Okay. what is next here? So what we care about is this second property here, is that the total variation distance is less or equal than two times the probability that x prime is different than y prime. So what is a proof of this? Okay, so let's start by writing, so the total variation distance of x prime y prime is the supremum over a of the probability that x prime is in A minus the probability of y prime is in A. Okay, so now this is for every set A in R, but here we can take A to be equal to every set contained in the image of X union the image of Y, which is a discrete set. Okay, so the idea is that because we are taking discrete random variables, we can take this summation over this discrete set, which we are just going to call I. Okay, so by noticing that these are discrete random variables, what we can say is that the total variation distance between x prime and y prime is going to be equal to exactly is going to be equal to the supremum of a subset of I of the probability of x prime in A minus the probability of y prime in A. But now, because these are discrete random variables, this is going to be, again, the supremum of A contained in I of the absolute value. Now, this guy can be decomposed as the sum of k in A, the probability of x prime is equal to k, minus the sum of k in A of the probability that y prime is equal to k. But now we can take this sum outside the absolute values and get an inequality. This is going to be less or equal. So here, we can put the summation like here. Now we can use the triangle inequality that says that this is less or equal than the supremum of A subset of I of the sum of k in A of probability of x prime is equal to k minus probability of y prime is equal to k. But now, taking this supremum over here, the best set that you can take, because you're summing all positive things, is equal to the sum of k in I of the probability of x prime is equal to k minus the probability of y prime is equal to k. Okay, so here we have an inequality, and now what we need to check is that this difference can be seen, can be bounded by 2 times the probability that x prime is different from y prime. So what I'm going to do is write this set as a union, a disjoint union. So x prime is equal to k is equal to x prime is equal to k, intersection y prime is different from k, union x prime is equal to k, intersection y prime is equal to k. Similarly, we can do y prime is equal to k, and we can decompose it in the same way. Y prime is equal to k, intersection x prime is different from k, union x prime is equal to k, y prime intersection y prime is equal to k. So what I'm trying to make you realize here is that if we write it like this set here is the same as this set here. And so because we are subtracting these two probabilities, this intersection disappears, and what we get is that this is equal to the sum of k in I of the probability that x prime is equal to k, comma, y prime is different from x prime, minus the probability that y prime is equal to k, comma, the probability that y prime is different from x prime. And now we can say that the difference between these two guys is less or equal than the sum. This is less or equal than the sum of k in I of the probability that x prime is equal to k, comma, y prime is different from x prime, plus the probability of y prime is equal to k, y prime is different from x prime. And now this is a disjoint union of this set, and this is another disjoint union of this set. So this is equal to 2 times the probability that y prime is different from x prime. Okay. So the idea of doing this proof is because we're going to use it for the following thing. So let's consider the following situation. We consider a coin that gets progressively harder to land heads. Actually, do I want this? So, okay, there's different ways of looking at this. So there's one way is to think of a coin that is gets progressively harder to land heads, but so the probability would be like, let's say, lambda over n, but we flip it and increasing number of times. Okay, so n. So basically, we have a coin that becomes that the event that the coin becomes a head becomes larger and larger. Smaller and smaller. So if I flip the coin once, the possibility I get heads becomes really small. Let's say that this is much smaller than 1. But we do it so many times, n, much bigger than 1, that what we expect is that this is distributed. So we care about what is the distribution of heads. Okay, so here I would say that we would get like, so here the thing would be let's say that, so morally what I'm saying is consider xn, or let's call it yn, which is distributed as a binomial with parameters n and lambda over n. Okay, so this is the distribution of heads of a coin that is really hard to get heads, but it has been flipped a large number of times. So the point is that we can show that this converges to, let's call it, so this converges to set, which is exponential of parameter lambda when n goes to infinity. Okay, so this will be a corollary of the following theorem. So morally, what we are like looking at this is what is the probability that you get a large number of heads. Okay, so even though you're flipping a really long, big number of times, the probability that you get a heads becomes smaller and smaller. So the point is that the scaling between how the probability is going to 0 with the quantity of tosses is giving you some behavior which is exponentially decreasing. Okay, so the idea is that this binomial here, which becomes harder and harder to track when n is large, in the end becomes something exponential. So morally, this corollary is telling you that you can see how the distribution of this guy behaves just by looking at this parameter lambda. Okay, so this is a corollary of the following theorem. So if xi are independent random variables, with Bernoulli distribution, and here we are going to have an even more general case. We are going to consider xi, which is distributed Bernoulli pi, with pi is a number between 0 and 1. And let S be equal to the sum from I equals to 1 up to n of xi, S be equal to the sum of these guys. So morally, what we are saying is let's start flipping coins in which each coin has their own probability. And P be a Poisson. Let S be equal to this, and let P be a Poisson random variable. With parameter lambda, which is equal to the sum from I equals to 1 up to n of pi, of the probabilities pi, then the total variation distance between S and P is less or equal, and I'm not sure there is a 2 here, the sum from I equals to 1 up to n of pi squared. Okay, so in particular, if we take pi to be lambda over n for every I, then what we get here is that P is distributed with lambda given by the sum of these guys. And here, what we would get is this is equal to lambda squared over n. Okay, so we actually have a quantitative distance between the quantitative bound on the distance between S and P, where P is Poisson and S is the times the amount of heads that we get out of these trials. Okay. So proof. The idea is to use the ideas that we have discussing in this class. So the idea is to introduce a useful coupling, for the random variables. Such that we can estimate the probability that S, comma P, S is different from P, is less or equal than the sum of Pi squared. Okay, so the idea is that we introduce S prime, which is distributed like S, and we introduce P prime that is distributed like P. And the way that we do it is, okay, so S is written as the sum of xi, and P, we are going to be writing it as the sum of yi, where yi are Poisson of parameter Pi. Okay, so if we take, so if lambda, if y1 is Poisson P1 and y2 is Poisson P2, then y1 plus y2 is distributed with Poisson P1 plus P2. Okay, and here we need y1 and y2 independent. Okay, so the idea is that xi are all Bernoulli independent variables with parameter Pi, and now yi is going to be Poisson Pi, where the Poisson Pi, the Pi is the same as the one coming from xi. And these guys are independent, so these guys are also independent. So we are going to come up with a pairing with a coupling, between xi and yi. Okay, so xi is Bernoulli of parameter Pi, and yi is Poisson with parameter Pi. Okay, so what are we going to do? We are going to define this coupling by the joint distribution. We only need to come up with a joint distribution, or a joint, let's call it mass function. Okay, so we are going to come up with f of xi yi. Okay, so f of x y yi of little x little y is going to be the probability of xi is equal to x and yi is equal to y. Okay, but now these are discrete random variables, so the only thing that we care about is the values for a discrete set. So we care about the probability that xi is equal to 0, yi is equal to 0, the probability that xi is equal to 1, yi is equal to 0, and then the probability that xi is equal to 1 and yi is equal to k, and this is for k bigger or equal than 1. Okay, so here we're going to put 1 minus pi. Here we're going to put e to the minus pi minus 1 minus pi plus pi, sorry. And here we are going to put pi to the k over k factorial times e to the minus pi. Okay, so this is a coupling which is not, so one of the things that we should note is that xi and yi are not independent. So xi and yi are not independent. So, and that's the main point of the coupling. So this is a remark which should be outside of this proof. Trivial independent couplings are trivial and usually don't help with interesting bounds. Okay, so one of the things that we said here is that, okay, so xi, the sum of these xi's is s, but there is the xi's are independent. Sorry, the xi's are independent, but it doesn't mean that p is independent from the xi's. Okay, so what we are doing is we are making a connection between this s and this p in such a way that we can measure this distance in a more accurate way. So if we made them independent, the bound would be trivial. Okay. All right. So what we can check is, okay. So why aren't they not independent? So what is the probability? So the probability that yi. Okay. So first of all, if we take this thing for the probabilities of these things, if we take this distribution, what we can actually check is that xi is distributed with Bernoulli value pi, and yi is distributed with Poisson pi. But if we look at the probability that xi is equal to 0 and yi, let's say, is equal to 1, this is equal to 0. Okay, so here I should have added this, the probability that xi is equal to 0 and the probability that yi is equal to k is equal to 0 for every k bigger or equal than 1. Okay? Which is different from the probability that xi is equal to 0 times the probability that yi is equal to 1, which are both different from 0. Okay? So then xi and yi are not independent. Now, the point is now we consider S, which is the sum of xi, and we consider P prime, which is the sum of yi, which this guy is distributed with Poisson lambda. This is by the previous property here. Okay. Now, if we want the total variation distance between S and P, this is going to be less or equal than 2 times the probability that S is different from P prime. But in turn, the probability that S is different from S prime is less or equal than the probability that there exists an I such that xi is different from yi. And of course, the probability that there exists one is going to be less or equal than the sum from I equals to 1 up to n of the probability that xi is different from yi. So the only thing to get this bound is we need to calculate what is the probability that xi is different from yi, and this is equal. Okay, so we have to sum from I equals to 1 up to n. Now we come back to this this thing here. So the probability that xi is different from yi is going to be the probability that xi is equal to 1 and yi is equal to 0, and the probability that xi is equal to 1 and yi is bigger or equal than 1. So this is a sum of the probability of xi equals to 0, comma yi. The probability that xi is equal to 1, yi is equal to 0, which is this thing here, plus the probability that xi is equal to 1, comma yi is equal to k, and this is the sum with k bigger or equal than 2. And now the only thing that you need to do is replace this into this expression. And so this thing here is the sum from I equals to 1 up to n of e to the minus pi minus 1 plus pi plus the sum of I equals to 1 up to n of the sum from k bigger or equal than 2 of pi to the k over k factorial times e to the minus pi. Okay, and now the point is that now we have a cancellation by summing these things up. You get e to the pi. Okay, so the point is that summing this up perfectly, this is equal to the sum from I equals to 1 up to n, sum from I equals to 1 up to n of pi 1 minus e to the minus pi. And now what we can use is that this this thing is less or equal than pi. Okay, so 1 times e to the minus pi is always less or equal than pi between 0 and 1. So then this is just less or equal than the sum from I equals to n of pi squared. And this actually shows the theorem that we were interested in showing. So I'll stop now because we have class right now, so I'll see you in a second.